My name is Stephen Day. I'm Stevu on GitHub, and this is Take Control of Your File System with Snapshotters in containerd. That's a longer title. You can see it on the thing, but I wanted it to look nice on the slide. I guess the question. This is the first time I've given this talk, and I wanted to give this talk a long time, and it's the first time it's got accepted. And so I apologize if it's not great, but hopefully we can get through it. The reason I want to give this talk is I want to provide a rough history of container file systems and the important parts and the way I see it. And I'd like to also introduce this really cool functionality we built in containerd that I think has a lot of potential called Snapshotters. And I'd like to kind of show it in detail and what some of the basic primitives are and how they can be used. And then somebody who's more creative than me can run with that. I mean, the two areas that I think it's interesting in is for builders, and it's already being, Snapshotters are already being employed in build kit. And then volume snapshotting. And hopefully I can show you why and prove to you through the talk. So thank you. The other thing I'd like to address before talking about this is why do we have all this complexity in file systems? And you'll start seeing it as I talk about some of the things like how Docker is built up, and then how the changes we made in containerd. And the whole goal here is just to build a root file system for a container. And it's wildly complex, but when you start going through all the parts, they're all there for a good reason. But the biggest reason is to reduce the storage requirements and increase workload density. This is the main concept that we're looking to do. So if I had a naive model and I just unpack everything on a container file and I have storage for each of my containers, my storage cost is O of n in the number of containers. So like, let's say I'm running 10 Ubuntus, I have to run 10 Ubuntu ISOs, and they all have to be independent. So what we really want to do with containers is, so that we don't have to have as many disks, and we can use most of that disk space for like application storage, is we want to converge to, so that all the containers use the same storage, and they're using the same data, and our storage cost is O of 1 with the number of containers that are running the same file system. So this is the whole problem, and this is why you see all the complexity. This is why you see the cool behavior in Docker and other container systems that are kind of come that are arm in arm with containers. So that's great. The other thing I want to touch on really quickly is just mounts. We've all seen them. Hopefully we can review them. And I'm going to use the term mounts in a couple of different ways. But the classic way is taking a device and then parameterizing it, say, ext2, and then mounting it on user local. And then there's also, so I have an example of a bind mount too, where I just take like my path and then bind mount it to varlib app. So like I can, in the first example, I take like a device and I say, mount this device here. In the second example, I take like a path and I mount it there. And this very simple thing, hopefully everybody's played with the mount command, right? Yeah, most people. Okay, good. So the entirety of all of this stuff is built up on this concept of mounts, and even in other operating systems that don't have mount, it's mount-like in a way. So hopefully, like we've developed a model that actually applies to different systems and different places. And even though they don't have mounts, we can still use the terminology mounts. And I'll explain later about how we use the terminology in mounts in containerd and how that can apply to systems that don't even have a mount syscall per se. The other big concept we'll see. And I hope people have seen union file systems. Union file systems are this concept where you can take two separate directories and then overlay them together, and then create a mount parameterized as overlay, and then see both of those things. So in this example, I have a layer 0 and a layer 1. Layer 0 is my base layer in this example. Or whichever way the arrows, it doesn't matter too much. But they merge together. Like layer 0 has bin, layer 1 has lib, and they merge together, and you have bin and lib. How those things merge together is another story, and I'm not going to go into that in this talk at all because it's complex, but there's good kernel documentation kind of, and you can play with it and understand how that behaves. But there's a whole bunch of different models to do it. So I don't know if this is right, but I think the first place we saw union file systems was maybe Plan 9. I don't know if if it was before that. There might have been other implementations. The concepts, once you start thinking about file systems, it's not that foreign, but Plan 9 played with it a lot, and they built an operating system around bind mounts and union mounts. And then following that is like UFS, and you see that in like BSDs and other things. And then the big two that you're probably familiar with are AUFS and overlay. And AUFS was really employed heavily by Docker. And then overlay is kind of the what is the current one that everybody uses, and I think it's called the overlay 2 driver. You've probably heard about that at some point. So the other kind of file systems that we're going to talk about today, and kind of inspired Snapshotters and containerd, is snapshotting file systems. And I struggled drawing this diagram, but the idea is that you have a single like volume, which is just a collection of data, and you can pull off these pointers from it. And so you can say, well, revision 0 points here, and revision 1 points here, points here. And even though the data might be shared that hasn't been touched yet, once you touch that data, it forks off, and that's what we call copy on write. And both union file systems and snapshotting file systems typically do some sort of a form of copy on write, but with snapshotting file systems, they'll typically consolidate data storage at the block level. So you'll have some sort of like B tree, and the top of the B tree will point in to either like revision 0 and revision 1, and depending on which tree you're in, you'll be able to see bin and lib, and they'll be completely unique. So as you do modifications to these two things, you can fork them off in different directions. Some examples of this are, again, with the Plan 9 folks, like Fossil. NTFS, I know, has some snapshotting support. The big ones now are ZFS and ButterFS. And then everybody uses Git, presumably. It's not a file system, but it's a very similar concept of kind of snapshotting, where I have like a commit points to a tree, and then that tree, you can have a bunch of different trees, and then you use your commits to define the relationships of the changes to that tree over time. So, so union versus snapshot. Why am I talking about this? You know what? One's not better than the other. They have different properties. They have different behaviors. Like union file systems, for instance, they allow modification of underlying data. So I can change a layer at the mid-level, and so I can like do an upgrade at one point, and then have everything else consumed from that. Whereas like snapshots are more static. But because of the properties of snapshots, they can typically handle more revisions. So like Git, sure, the repository gets slow to push and pull, but it will handle a lot more revisions, say, than like overlay, which is going to be limited to like I don't know, 100 or so. I mean, you can push boundaries depending on how you actually form the mount command, but you're very limited in the number of revisions you can actually represent inside of a union file system. But the thing is, both of them are copy on write, and both of them for containers can be represented with a shared data model. And that's kind of and seeing that in the way containers behave, and in the implementation of Docker's graphdrivers and other systems, we can kind of define a common way of saying, okay, well, let's look at union file systems and snapshot file systems as the same way under this like snapshot model, and we can build up all of those things. So stepping back a little bit, I want to talk about the Docker storage architecture, because this is where a lot of this came from. And it's very complex. There's like a daemon on top, and then there's this like reference store, and it references images, and those images have like image configs, and then they join together at this thing called a layer store, which then finally gets down to a graph driver. And if you ever looked at this interface inside of Docker, it integrates pretty tightly with containers. It integrates pretty tightly with images. It integrates tightly. So like both containers and images have references into the graph driver, and the graph driver actually represents those IDs directly. So it's very tightly coupled. You can do pluggability with it, but all of your life cycle is tied to your runtime with the containers. So like these are some of the problems with the graph driver model, and I'm not going to go too deep into this, but like one area is it's inflexibility. It's really hard to experiment because like you want to experiment with file systems, but like I'm more of a file system guy than a container guy, and I want to play around with file systems, but to play around with graph drivers, you have to have container stuff. So so it's very hard to experiment with new models that might be take a few minutes to implement on a file system, but once you start getting containers involved, it becomes more complex. The other thing I talked about a little bit on the last slide is how tightly coupled it is. So like the container lifecycle is an example. If you've ever ran into like deadlocks or like, oh, I can't remove this container because of some sort of references, it's because of this massive reference network inside of the Docker daemon. It's also really tightly coupled with the image format. So the image format and the layers are actually it's defined as the actual on-disk format of the AUFS change sets. So there's this like tar file in the middle that's actually you just tar up the AUFS representation. Well, that's really efficient and it's really great, but it means that every other graph driver needs to convert between AUFS, this AUFS format, and also it makes it hard to increment on image format. So like you can't say, well, I want to try out Git for some reason, or I want to try out a new tree thing or something like that. It's a lot easier. It's really, really hard to do in Docker because you're so tightly integrated with that format. And then, as I touched on before, is the primitive is just simply can't be used outside containers, right? So like you're tied to that life cycle, so you're tied to using containers. So stepping back, hopefully I've covered much of the words. I just want to say what containerd is. You could have come to my intro talk, or I'm doing another deep dive on Friday, and you can learn all about it. Or you can come and say, hey, what's containerd? Or you can look it up on the internet, whatever. But at the base of it, it's a container runtime manager. It powers Docker. It can do Kubernetes CRI stuff, but it provides the primitives to implement containers. And it increments on the internal architecture of Docker and provides that. Scott Colton also has a great talk on containerd showing what it can do, what it's capable of. Check out the URL, containerd. You should be able to find this quite easily. So this is the architecture of containerd, and at the top we have the interfaces like gRPC, and in the middle we have these gRPC and Prometheus metrics, and then in the middle we have all of our services. And this talk is really going to talk about just the Snapshotters and how that integrates with the storage system, but really just more about Snapshotters and what they do and how they work and the life cycle and how we represented them. This diagram is just the simple container storage architecture. So basically, there's a metadata store which holds like containers and images, and those just reference out to snapshots and then actual image content. And so these metadata stores actually provide the linking between the snapshots. So you don't identify a snapshot based on the image you pulled it with. You just say, this snapshot has this ID, and I have an image record that points to this ID. And however you want to build that relationship, you can do. It doesn't matter. The IDs and the snapshotters are completely opaque. So all of these are based on simple layer relationships. So like you make a change, you make some, or you pull off a layer, you make some changes to it, you commit back your changes, and then now you have a layer relationship. The interface is much smaller. It's much more focused. I don't have the graph driver interface, but believe me, it's large. Like I said before, non-opinionated string keys. And then the biggest piece, I think, will improve performance and behavior under a lot of other conditions is the fact that we've externalized the mount lifecycle. So the graph drivers and Docker actually perform the mounts. So you say, hey, okay, we'll mount this container for me and give me a read-write image. And then you say, okay, all right, and then you get it back, and then you have this handle, and then you got to make sure to unmount that handle. Whereas with the Snapshotters, what you get is just a mount. You get this reference object, and you can then mount the file system as you see fit. And so now you can tie it to the life cycle of the thing that you're actually using it with, which is typically a container, or it could be a build. We also support something called leases within containerd, so you can define like a transaction for when this snapshot is actually available. Like I said, there's no mounting. There's no actual mounting. It just returns mounts, so you can do it in user space. You could do all sorts of other cool stuff. You don't actually have to do a syscall mount. You could have a Snapshotter that implements URLs, and then it does something with URLs or something like that. You'd have to have special mount support for that, but you can do that. They're always explicitly active and explicitly committed, so there's a life cycle, and I'll show you that. And then all of the life cycle is represented by a command. And so it's very easy to use, very simple. There's no, you don't get back an object for each snapshot, and that ensures that you don't have these like arbitrary life cycles that can kind of get in the way. And then the reference keys are chosen by the callers. And we don't actually integrate any of the formats. All of the diffing that you would do in Docker to get images or in layers within Docker is completely external to the Snapshotters. So I can define completely new image formats, but still use Snapshotters with them. And we provide lots of libraries to do that. Conversely, our diff system doesn't require you to use Snapshotters. So you can just take two arbitrary directory paths on the file system and then diff them and generate a layer. So you can build a lot of primitives from that. So this is the general snapshot lifecycle, and hopefully this isn't too opaque. But on the the first step here is we have a committed P0, and then we call prepare on it, and we give it a name A. And then you have A, and then you can do things to it on that arrow going down to A prime, and then you have A prime, and you call commit on it. And that will create P1, and then create this little, can we see that arrow? So that'll create this relationship between P1 and P0. And then you can go through that again. You can do a prepare, and then grab P1, and then you get A double prime, do something to it, commit it, and then you would get P2, which has a relationship with P1. So is that's pretty clear? So here's like an example, and I'm going to do this in a demo here in a moment. I haven't done this demo live yet, so hopefully it works. In this one, we're basically saying, okay, well, let's prepare. We're going to call it active 0 because it's going to be in the active state. And then we're going to actually mount it. So we're going to mount active 0 onto a location on the disk. And then we'll touch hello. That's missing some path stuff, but it should be target/hello. And then we'll unmount the target, and then we'll commit that back in, and then we have a snapshot. Then we can investigate that. So we can list these snapshots. We can do a tree on it. I don't know if you ever saw Docker tree. It was a very cool command, but it had a lot of internal problems because of the way Docker's built. We can support that directly with snapshots. It's really useful, really cool to look at, and I'll show you a few examples about it here in a moment. And then we have a mounts command. So I can run a container, and then I can stop it, and then I can mount it outside of the container. I can fiddle with it, and then I can unmount it, and I can start the container up with those changes. So you can imagine all sorts of cool stuff you can do with build, and there's operational things you could do. You could grab dumps without having to do an exec. There's a lot of things. So hopefully, let's see if we can get this to work. All right, so I have an empty container D here, and there should be no snapshots. Okay, great. So what we're going to do is we're going to create a snapshot, and so all of the things are pretty well documented here. We have like commit, diff, info, and I'll show you how this relates to the actual internal interfaces here in a second. But we can do a prepare, and when you do a prepare and you don't give it a parent, it's just going to start with an empty directory. So we'll call this active 0, just like our example in the slides. And, ooh, okay, it worked, sweet. All right, so now this should show up, and we see that we have active 0, and it is active. And, well, okay, so what does that mean? How useful is that? Well, okay, it's not that useful yet. So I have a temp my path, and what I'm going to do is I'm going to mount this. So there's a ctr snapshot mount command. And so we'll mount on temp my path, and then we will do active 0. Whoops, active 0. And so actually what this did is it just prints a mount command. I didn't want to build actual mounting into there, so it just gives you the command. And then you can do this wildly dangerous thing called xarg sudo. It's so much fun. So we'll mount that. And we can actually see, well, okay, it doesn't look like there's anything. It's an empty directory. I already was forthcoming about that. And you can see here, that's that's the mounting of it. It's just a bind mount kind of right now because there's no changes in it. But we can do a what did I say here? We'll go ahead and touch. So we can do a touch. So we can do sudo touch temp my path hello, and then we can see that in our path. And let's get that tree command working nice. Okay, so now let's unmount that. So we'll unmount temp my path, and we have to tell it to do it hard with sudo. And then so now what do we have? We still have this active snapshot. Nothing's changed about the snapshot. It's just the on disk state. So like containerd doesn't know about this yet. So what I'm going to do is a commit command. And a commit command it's just like the prepare command, except it's kind of the other part too. And I'll show a code example about how this works in a more complicated scenario. So we just call commit, and then now we can list our snapshots, and we can kind of see what happens here. Where did that go? Snapshot ls, and then you can see here, oh, foo has been committed, and we no longer have our file system path there. There's nothing there because we unmounted it. So what we can do next is let's create another one. But this time, when we create our, when we prepare, we are going to define foo as the parent. So now I can do that same fancy mount command. Where'd it go? What mount? Let me just type it out. CTR snapshot mount, and then it's going to be temp my path and active 0. Since we're using the same reference as before, even though it's a different one, so that's our mount command. So notice that it changed quite a bit, right? So now, since we're actually descending from foo, we actually see that we have an overlay mount, and you can see it's like type overlay, and it says lots of things. It defines a working directory, lots of implementation details about overlay, which you can go read about. Well, I ran out again, but actually, let's do the fun thing and pipe it to xarg sudo. So now we have it mounted. Whoop, there's hello, and we're back to it. The cool thing now is we can do CTR snapshot tree, and we can see like, oh, cool. We have a relationship between active 0 and foo. So that's we're in business. So now we have an actual like layer relationship, and if we ls these, we can see that we have two. We have an active one called active 0, whose parent is foo, and then we have a committed one called foo, which is the base layer. So now I can go and I can do the same kind of thing where I touch into. We're going to touch world this time, and then we should see tree, my path, and then we got hello and world, and then. We can go ahead and unmount that, and temp my path. Whoops, yeah, we got to tell it to do it harder than that, and then we can do a commit. So CTR snapshot commit, and then we'll do what's the ordering here? So we're going to commit into bar, and then we're going to commit active 0, active 0. We're going to commit that into bar, and then now what happens is I have, so if we look at snapshot tree, so now active 0 has been shut down because we committed it. Like it acts like active snapshots act like a transaction, and then we've committed it into bar. And if we list that, and when we look at that, we still have the same, like bar has foo as a parent, and they're both committed snapshots. And so it's like, what I did here is basically built up a container file system from scratch from the command line. So I think it's cool. Okay, so moving on. So a little bit, so the internals, so if you can see that okay. So this is the interface of the Snapshotter, and I have a link to it at the end, and if you really want to understand it and all the operations, go read the Go doc. We spent a lot of time ensuring the model was up to snuff and well defined. But the interface is mostly method driven. You can see we have string keys everywhere in context, but the big takeaway here is we have three kinds. We have the active and committed, which I showed you, and then we also have what are called views, and so these are read-onlys, and that allows snapshotters to say, well, if it's read-only, I can mount it differently, or I can do different data sharing, so we know that modifications aren't going to come through, and you can actually express that in the system. And then just like I showed you on the command line with the snapshot ls, you can see that that info is represented in this structure, and so we can actually stat these. That is not what I expected to do. Okay, so we can actually stat these and get back the info. So you can actually build up, so that tree command, what it does is it walks down and then gets all the info structs and then assembles a tree. And so you can actually see the relationships inside of your file systems. How much time do I have? Okay, so this is a really short code example that I took. It's a lot longer in the implementation because we have to handle errors and do other things with like chain IDs and whatnot. Those are just implementation details. But here we see the interface in action, and it's quite simple. You take you prepare from a parent, and the parent is just it's just a string. And it can start empty, and then you get these mounts set, and then you hand it into this thing called a diff.applier. And what that diff.applier is doing is taking a layer blob, like a tar file, and then mounting everything, applying it, and then doing all the magical image format things, and then gives you back a diff reference, and I don't remember what that is actually, but then it unmounts everything, which is like super key, right, is that you do something, you mount it, and then you unmount it. That way you don't have all these mounts hanging around your system and causing later problems for you. And then you simply take that and you commit it, and that's it. And then you can apply this in a loop, and that's how you do layered diffs. And this is right in containerd in the rootfs package. If you're curious, it's really simple, really easy to understand, and it's quite a powerful concept. This apply function, this diff.applier, is implemented to deal with like OCI style or Docker style containers, but you could do almost whatever you want in there. And like I was just doing touches on the file system. So a couple of considerations. Snapshots are a generally good model. It's pretty simple. Hopefully, I've explained it in a way that can be consumed. But I think we have a really good model because I think it will work for lots of different scenarios without modifications to the actual snapshotters. We can modify things around the snapshotters so that they'll work in different ways. So you say run a snapshotter inside of a container, and you could get like UID mapping. So for rootless, I don't think the snapshot model needs to be changed, but I think all that needs to be done is how you actually do the mounts and UID mappings that do present problems for rootless containers. And I'm not an expert in that area, but there are people here who you could probably ask questions about the problems that might come up. The other cool thing that I don't think anybody's doing yet, but would be great and we can help out with is daemonless snapshotters. So like this is just a snapshot package. There's a test suite. You can just import it and play with them in Go and do snapshotting without the daemon. And so I think there's definitely applications for builders that are based on like native snapshotters and stuff like that. So there's lots of interesting things I think that can be built here. I think that you could build a Git snapshotter. It wouldn't be very good for production, but it would be kind of a fun thing, and I think that would be, right in the right up the alley of snapshotters. So currently in containerd, we have 5 implementations. We have Btrfs, overlay, ZFS, AUFS, and what we call native. And native is just where you take tar files and apply them and then copy the whole directory over. And it gives you POSIX performance at the cost of, remember the diagram I showed you at the start where every container has its own store, like that's the kind of O of 1 worst case, but some people need that for certain things, like where you can't perform mounts on the file system is a great example. There's also, we have a full test suite, so graphdrivers in Docker, like they're tested, but like there's not like a unit or functional test. You can't just like modify the graph drivers and then run a couple of tests and know everything's working. You have to like test them in the integration suite. And I don't think there's actually a full battery of tests. They're just going to get tested through the CLI, so you can't just run those section of tests. With the Snapshotters, we built a fully verifiable, not fully, that's the wrong word, like a full integration test suite that you can just run against your Snapshotter. So you can implement your foobar Snapshotter, and then you'll know if it's working or not. And we test all sorts of great edge cases in there to make sure that your Snapshotter follows the model. So going further, again, containerd project, experiment, file bugs, talk to us, yell at us, whatever you want. Do it nicely, though. And like I said, this link is a little messed up, but I'm sure you can figure it out by typing it in. But it's the Go doc to the snapshots package in the Snapshotter, and it defines in detail all of the pieces of how these operations work, how they should perform, and any kind of issues with those. If you're more curious about containerd, come to my talk on Friday, and come and ask about it. I do talk about Snapshotters there. I'm gonna for this talk, I'm gonna almost do full demo mode, and we can just you can ask questions about how things work, and I can play around and show different things. So I can show how the Snapshotters work with other stuff too. So yes, with that, I think I've 5 minutes. Yeah. So if there's any questions, that would be great. And thanks for coming to the late talk. I know it's late in the afternoon, and I'm jet lagged, so I'm sure there's other people here. So thanks for coming. So are there any questions? Oh, okay.
Hi, thanks for talk. I still don't get it. So you use overlay, and with overlay you've got a lot of mounts, and now you just jump over it and take all the diffs and take another overlay snapshot and put everything in it that you only have one mount? Or what's the big difference between the old stuff in Docker using overlay too and this approach, just to get it?
They're pretty similar. And Docker usually only does a single mount for each layer, and it's defined like in that mount command. The main difference is just the fact that I don't have to run a container to get this mount, and I can do this. I can pull this mount directly out of the containerd with a command line tool. That's like the big difference, and I can safely mount and unmount that and work and integrate with other systems in that way. Does that answer your question? Okay. Anything else? Okay. All right. All right. Well, thanks everybody for coming.